Why is PVC-O pipe so difficult to produce? If you have experience with PVC-O, you probably know that making one good pipe is not the real challenge. The real challenge is making thousands of meters of pipe continuously at high output with stable OD, stable wall thickness, consistent orientation, and consistent mechanical performance. High efficiency, stable PVC-O pipe production requires a completely different level of system engineering. I often hear people comparing a PVC-O line with a conventional PVC-U line by asking, what is different? Is it just the orientation machine? No. The difference is much more fundamental. For a functional high-output PVC-O line, almost every stage of the process has a new requirement. Let's start from the beginning. Extrusion and plasticization. The dry blend has to be plasticized uniformly, with stable melt temperature and melt pressure. Because if the feedstock pipe entering orientation is already unstable, the orientation process will only magnify that instability. Die and sizing. Feedstock pipe needs excellent dimensional uniformity. The geometry of the die, melt distribution, sizing system, and cooling all influence the starting condition for orientation. Cooling is no longer simply about getting the pipe cold enough. You need to control the thermal history of the preform. The temperature distribution through the wall matters because the material entering orientation must have a controlled and repeatable thermal condition preheating. This is one of the most critical stages. You need to bring the pipe back into the pipe orientation window without creating excessive temperature gradients through the wall. For thick wall pipes, this becomes particularly difficult because the inner and outer layers do not heat at the same rate, orientation, and expansion. Now you have to control the biaxial deformation itself. Expansion ratio, axial stretch, internal pressure, deformation speed, and cooling have to work together. Haul off. The haul off is no longer simply pulling the pipe at a certain speed. Its speed is directly connected to the deformation process. Any fluctuation can influence the orientation, ratio, and final dimensions. Even cutting becomes more demanding. The pipe has already undergone substantial orientation and residual stress development. Cutting must therefore be stable and accurate without generating unnecessary deformation or damaging the pipe end. And finally, socketing. The socketing process has its own requirements. The pipe has already been oriented. Now you are locally reheating and deforming the material again. You need to control the thermal cycle and forming process without compromising the mechanical properties that you worked so hard to create during orientation. So when we talk about PVC-O extrusion equipment, the technical requirement for every stage is on a different level. From PVC-U, and the higher the pressure class, the larger the diameter, the thicker the wall, and the higher the output, the more demanding this integration becomes. Secondly, the orientation and expansion process itself requires a very specific operating technique. After the pipe is extruded, PVC-O is not simply cooled down and hauled off like conventional PVC-U. The pipe has to be reheated into a very carefully controlled orientation window and then expanded and stretched. This sounds straightforward. In practice, it isn't. The operator has to control the relationship between preheating temperature, expansion ratio, internal pressure, axial stretching, haul-off speed, cooling intensity, and the actual orientation behavior of the pipe. And these parameters are highly coupled. For example, if the pipe is slightly too cold before orientation, the material may not have enough molecular mobility. You increase the deformation force, and instead of achieving uniform orientation, you may start to create localized stress concentration. If it is too hot, the opposite problem appears. The material becomes too soft, relaxation increases, dimensional stability becomes worse, and the orientation that you have created is more difficult to retain. So the objective is not simply heat it and stretch it. The objective is to create the right thermal and stress conditions so that molecular orientation occurs uniformly through the wall thickness and along the entire pipe length. Moreover, keeping OD and wall thickness stable after orientation is much more difficult than it looks. This is one of the biggest challenges in industrial PVC-O production. Before orientation, you may already have a relatively stable extruded feedstock pipe. But once you start expanding it, you are amplifying every small variation that already exists in the preform. Imagine you have a very small wall thickness variation. Before orientation, during expansion, the deformation is not necessarily distributed uniformly. A slightly thinner area can deform more easily. A small variation upstream can become a much larger variation. After orientation, the orientation process doesn't eliminate upstream variation. In many cases, it makes that variation more visible. That's why achieving stable OD and wall thickness at high speed is such a difficult engineering problem, and this becomes even more challenging when we move toward thick wall, high pressure PVC-O pipes, which is the trend and future of PVC-O pipes. I believe the real benchmark for a PVC-O line is not, can it produce PVC-O pipe? The real question is, can it produce PVC-O efficiently, continuously, and repeatably? Can the OD remain stable? Can the wall thickness remain stable? Can the orientation remain uniform? Can the process tolerate normal variations in raw material and environment? And most importantly, can you maintain all of this while increasing output? That is where the real engineering challenge lies. Firstly, we should look at the entire process chain, from plasticization and preform quality, all the way through cooling, preheating, orientation, haul-off, cutting, and socketing. More importantly, at the same time, at Alive, we produce PVC-O pipes every day. We accumulate massive day-to-day hands-on experiences regarding how to make PVC-O pipes efficiently. PVC-O is not just machine. It is a process system. And the better you understand the interaction between every stage, the closer you get to truly stable, high-efficiency PVC-O production. I'm Chelsea. This is Chelsea on Pipe Extrusion. See you next time.